Broadly, HDFS architecture is known as the master and slave architecture. So how does it work? A master node, that is, the name node, is responsible for accepting jobs from the clients. Its task is to ensure that the data required for the operation is loaded and segregated into chunks of data blocks. HDFS exposes a file system namespace and allows user data to be stored in files. A file is split into one or more blocks, stored and replicated in the slave nodes, known as the data nodes. The data blocks are then distributed to the data node systems within the cluster. This ensures that replicas of the data are maintained. Data node serves read or write requests. It also creates, deletes, and replicates blocks on the instructions from the name node. We discussed in the previous topic that it is the metadata which stores the block location and its replication. There is a secondary name node which performs tasks for name node and is also considered as a master node. Prior to Hadoop 2.0.0, the name node was a single point of failure, or SPOF, in an HDFS cluster. Each cluster had a single name node. In case of an unplanned event, such as a system failure, the cluster would be unavailable until an operator restarted the name node. Also, planned maintenance events, such as software or hardware upgrades on the name node system, would result in cluster downtime. The HDFS High Availability, or HA feature, addresses these problems by providing the option of running two redundant name nodes in the same cluster in an active-passive configuration with a hot standby. This allows a fast failover to a new name node in case a system crashes or an administrator initiates a failover for the purpose of a planned maintenance. In an HA cluster, two separate systems are configured as name nodes. At any instance, one of the name nodes is in an active state, and the other is in a standby state. The active name node is responsible for all client operations in the cluster, while the standby simply acts as a slave, maintaining enough state to provide fast failover if necessary. An HDFS cluster can be managed using the following features: Quorum-based storage and shared storage using network file system. Quorum-based storage refers to the HA implementation that uses Quorum Journal Manager, or QJM. During this implementation, the standby node keeps its state synchronized with the active node through a group of separate daemons called journal nodes. Daemons are long-running processes that typically start up with the system and listen for requests from the client processes. Each daemon runs in its own Java Virtual Machine, JVM. When any namespace modification is performed by the active node, it durably logs a record of the modification to a majority of the journal nodes. The standby node reads the edits from the journal nodes and constantly watches for changes to the edit log. As the standby node sees the edits, it applies them to its own namespace. In the event of a failover, the standby ensures that it has read all the edits from the journal nodes before it promotes itself to the active state. This ensures the namespace state is fully synchronized before a failover occurs. In shared storage using NFS implementation, the standby node keeps its state synchronized with the active node through an access to a directory on a shared storage device. Now, in the next screens, we will discuss in detail the components of HDFS, which include NameNode, DataNode, secondary NameNode, and file system namespace. The NameNode server is the core component of an HDFS cluster. There can be only one NameNode server in an entire cluster. NameNode maintains and executes the file system namespace operation, such as opening, closing, and renaming of files and directories, which are present in HDFS. The namespace image and the edit log stores information of the data and the metadata. NameNode also determines the linking of blocks to data nodes. Furthermore, the name node is a single point of failure. The data node is a multiple instance server. There can be n number of data node servers. The number depends on the type of network and the storage system. The data node serves, stores, and maintains the data blocks. The name node server provisions the data blocks on the basis of the type of job submitted by the client. Data node also stores and retrieves the blocks when asked by clients or the NameNode. Furthermore, it reads, writes requests, and performs block creation, deletion, and replication on instruction from the NameNode. There can be only one secondary NameNode server in a cluster. Note that you cannot treat the secondary NameNode server as a disaster recovery server. However, it partially restores the NameNode server in case of a failure. The secondary NameNode server maintains the edit log and namespace image information in sync with the NameNode server. At times, the namespace images from the NameNode server are not updated. Therefore, you cannot totally rely on the secondary NameNode server for the recovery process. HDFS exposes a file system namespace and allows user data to be stored in files. HDFS has a hierarchical file system with directories and files. The NameNode manages the file system namespace, allowing clients to work with files and directories. A file system supports operations like create, remove, move, and rename. The NameNode, apart from maintaining the file system namespace, records any change to metadata information. Now that we have learned about HDFS components, let's see how NameNode works along with the other components. NameNode maintains two persistent files, a transaction log called an edit log, and a namespace image called an FS image. The edit log records every change that occurs in the file system metadata, such as creating a new file. The NameNode's local file system stores the edit log. The entire file system namespace, including mapping of blocks, files, and file system properties, is stored in FS image. This is also stored in the NameNode's local file system. When new data nodes join a cluster, metadata loads the blocks that reside on specific data node into its memory at startup. Metadata then periodically loads the data at user-defined or default intervals. When the NameNode starts up, it retrieves the edit log and FS image from its local file system. It then updates the FS image with edit log information and stores a copy of the FS image on the file system as a checkpoint. The metadata size is limited to the RAM available on the NameNode. A large number of small files would require more metadata than a small number of large files. Hence, the in-memory metadata management issue explains why HDFS favors a small number of large files. If a NameNode runs out of RAM, it will crash, and the applications will not be able to use HDFS until the NameNode is operational again. Data block split is an important process of HDFS architecture. As discussed earlier, each file is split into one or more blocks stored and replicated in data nodes. Data nodes manage names and locations of file blocks. By default, each file block is 128 megabytes. However, this potentially reduces the amount of parallelism that can be achieved as the number of blocks per file decreases. Each map task operates on one block. So if tasks are lesser than nodes in the cluster, the jobs will run slowly. However, this issue is lesser when the average MapReduce job involves more files or larger individual files. Let's look at some of the benefits of the data block approach. The data block approach provides simplified replication, fault tolerance, and reliability. It also helps by shielding users from storage subsystem details.
Hey, want to become an expert in big data? Then subscribe to the Simplilearn channel and click here to watch more such videos. To nerd up and get certified in big data, click here.